things are back to them. Okay. Yeah. So, for me, this started with this paper of the 5 people here. And yesterday you heard the talk by Anna. I missed it, but I couldn't see it today on the YouTube. Maybe it was not there. But and there's a series of papers, and the one that I'm going to use mainly is the first one. But this is a very interesting story. And so I want to explain to you what our triangular partition, you see one here. That's a triangular partition. And the gang, the 5 gang, B, blah, 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 MS, that I had previously, they call it partition under any line. So I'm going to show you, explain to you what this means. So I'm looking at a Ferraz diagram. You know, when you have dots, it's a Ferraz diagram. And so you have a Ferraz diagram like this. And I want to say that it's convex. Oh, no. I want to explain what the notion of convex. Now, this one is not convex, but its complement is convex. Oops, what's happening? Yeah. Its complement, the blue part, that goes to infinity, is a convex diagram. What does this mean? It means that if you look at the convex all of all the blue points, and you look at the integer points inside this convex all, what you'll get back is exactly the blue points, so no more. And so the complement of the yellow is a convex diagram, and the yellow is a concave diagram. So the yellow part, I'm going to say that it's concave because its complement is a convex. So that's a concave diagram. It looks like a concave region. And okay, so now let's go on to triangular partition. So a triangular partition is in yellow here, and it's a partition such that its diagram is both concave and convex. So its complement is convex as before, and itself, the yellow part is convex. So it's the yellow points are the only integral points inside the convex hull of the yellow points. So that's, I'm going to say that the yellow part is a triangle. So, and as usual, we look at the diagram as a set of boxes. So I've defined to you what is a triangular partition. Whoops, I clicked too much. And here you see all the small triangular partition organized as usual in the Young lattice, so by containment. And there's a phenomena that is very beautiful here. First, so if you look at it, you see that it's planar. And the faces are very nice. Many are quadrangle, and then there's a 6 side and 8 side there, and this goes on. And there are larger and larger faces as you go up. So the Young lattice of triangular partition here is, oh, and also if you look at the level, so that's in red, you see a level of this lattice. So these are all partition of, I guess, 7. And it's a total order, and that's the dominance order. So the dominance order is for triangular partition is like this, level of the triangular Young lattice, which is planar. And that's nice result that, so the Hasse diagram of the triangular young lattice is planar, and you can see more about the proofs of this and other properties in a paper with Michael Mazin that's on arXiv and should. I'm hearing something, maybe someone has an open mic. And I'll give you a sketch of the proof. So you look at lines that cut off a cell from the rest of the plane. So here you have a line that cuts off this cell from the rest of the plane. And there are many such lines. And for each of these lines, I'm going to look at the two coordinates, the y-axis coordinates and the x-axis coordinate in the other way. And I'm going to plot these in a new plane. This is the RS plane. So this green curve corresponds to all possible lines that cut off this given cell. And if you, so that's illustrated by the animation I just showed. So if you change the slope of the cell that cut off this, you go along this curve. And now you look at all the cells, and for each cell, you compute this curve. So each cell of the plane will give a green curve, and if you plot all this, you get this picture. So that's the curves. That's the curve that below this you have no cells, and above it you have one cell. That the bottom cell. And now, if you pass this curve, you get another cell. If you pass this curve, you get another cell. And if you go along the RS plane like this, you get regions. The space is cut off into regions, and each region is very nice. So you have typically you have regions with 4 sides, but you might have regions that have 3 sides, like this, or like this. So the difference here is that the one side, say, was on the bottom and then on the top for the other one. So, and the young lattice is here, because if you go from if you put a point here, it's a diagram inside each of these regions, and you do the usual dual graph, say, of this, you get the young lattice. And if you look at it a bit more, the reason why you have these, what you see is that given a triangular partition, typically there are only 2 cells that can be added to a triangular partition so that you get a larger triangular partition. Two very specific cells in general. Sometimes there's just one. And if you study this and get the properties of this, you prove the theorem that was mentioned earlier. So now you know what is a triangular partition. So I'm going to pick a triangular partition, tau for triangular, and I'm going to consider enumeration of tau Dick paths. So the tau is the overall partition that's going to help me talk about the Dick paths. So that's a very classical way of doing things. So I fixed tau, a yellow triangular partition. Believe me, this one is triangular. And then I look at all partitions that sit inside tau. Oh, by the way, I use French notation because Cartesian coordinates are natural in French notation. If you use English notation, you have to look at all of this upside down in the mirror, and it's very complicated. And then you don't use Cartesian coordinates. So someone is talking. Maybe someone forgot his mic on because I get feedback. Okay. So, what I'm going to say is that choosing a Dick path of shape tau or inside tau corresponds exactly to choosing a subpartition. So counting Dick paths is counting subpartitions. And if you want to see this as a path, think that you're starting somewhere here and you follow the boundary of the green. And then if you think that you have a diagonal this way, this is the classical way of looking at Dick paths. So if you didn't know about Dick paths before, this is great because you're not mixed. You use my definition, and the definition is easy. If you know what's a partition, you just look at a partition that's contained in tau. So that's a Dick path. Okay, I'm gonna QT enumerate these paths. I looked at Jim's talk of yesterday. He already introduced many of the notions that are here. Maybe I'm gonna be too fast. If you didn't follow Jim's talk yesterday, you will have to go on YouTube and look at the details. But so I'm going to call A tau the enumerator for all the possible Dick paths. So the sum is over alpha contained in tau. Alpha is changing. And I'm counting these Dick paths with two parameters, Q and T. So this is going to be a polynomial in Qt. And Q is counting the number of non-green cells. You remember alpha is green inside yellow tau. So the cell that stay yellow, that's counted by Q. So it's the area contained outside of alpha. And then there's the dim statistic for paths. And there's several ways of defining this. And if you want to understand why the definition is like it is, I urge you to go and see the paper with Michael Mazin, where we explain that this is very geometrical, natural from the point of view of triangular notions. But I'm going to do it, say a bit fast today. So bear with me. Imagine that you know what this dim statistic is. I'm just showing it to you now. I'll explain next slide. So you choose a yellow triangular partition, and you look at all the partitions that are contained in it. There are 5 of them. That's a Catalan number. And so nothing, 1, 2 cells side by side, 2 cells, one on top of the other, and everything. And then Q is counting the yellow. So Q3, Q squared, QQ, and nothing. And then T is counting some of the green cells. That's the dim statistic. And the number of these special cells is the parameter, the exponent tau. Now, how are these defined? So you have a triangular partition. A triangular partition is a triangle. This is the hypotenuse of the triangle, rectangle, the classical rectangular.
Right triangle.
Right triangle, yeah. And the hypotenuse has some slope, and I'm looking at the vector which is normal to it. And there's some, you could play a bit with it, but I'm going to explain. And then I look at one cell, any cell, inside the green part. And for this cell, I look at its leg that goes up, the blue cell here. If you are colorblind, you might have trouble, but this is the number of cells above C, which are in the same column, and then the red cells, which are the arm of the C. And so L, oops, I'm going to show you this better. So you have C, the same cell C here, the blue cell above, the red cell to the right, and I'm going to calculate two slopes, which are two approximation, let's say, of a slope for the triangular shape that would have this side above, vertical side, and then bottom side. And so there's the red approximation that is obtained by taking the corner of this blue and the corner of the next stress cell to the right of the arm. And so this is the red. And the vector that is here, I'm just recording it. Imagine that its coordinates have sum up to 1, and I'm calculating just the first coordinate that sum up to 1. That's sufficient. So T minus is essentially giving the slope of the vector, which is orthogonal to this, and it's calculated by L is the leg length, L, divided by L plus A plus 1. So AC, LC plus 1, this sum above is just the hook length of that hook. And LC is the length of the blue part here. And you do the same calculation for the other way of doing this, adding one box to the leg and keeping the original box of the arm, and you get this approximation. Now, these two approximations are two approximations of slope, and the DINF, and C is going to be a DINF cell if and only if this yellow slope globally for the tau sits in between. So up. So if you have this, that means that this is a DINF cell. So now, so DINF cells have to do with triangularity, and then for a given alpha sits inside tau, you look at each of the cell. If it's a DINF cell, you keep it, and if you're not, you don't count it. And that's the definition I was giving to you a minute ago. And DINF statistic is the number of these. Okay, so now we know how to calculate it. This, and I want to go to the next step, which is fun for me. It's this polynomial has a very beautiful structure. It's it's the sum of two Schur functions calculated in two parameters Q and T. So this is S3, the homogeneous symmetric function, if you want. Calculate at QT, so it's the sum of all polynomial of degree 3, and this is S11, elementary symmetric function, if you want, calculated at QT. So this expression is Schur positive. That's important. So what happens is that for all triangular partition, if you calculate this QT polynomial, it is Schur positive. We know how to prove this in many instances, but I'm not sure if we have a proof for every cases. So I'm going to say that some cases have been shown. Okay. So now I'm going to slightly generalize what I had before. I'm going to calculate something for any vector v in of length n with integer coordinates that might be positive or negative or zero, whatever. And that's going to be given by, I'm going to calculate a polynomial in Qt using this vector. And you see where I'm going, because if this B is correctly chosen, I'm going to get back what I had before, because the notation is very similar. But the definition is clear if I give it for any V. So AVQT is going to be a sum over V is of length n. So I'm going to sum over all partition of length n. So V is not a partition, it's just a vector. It has some length n. I'm looking at all partitions of n. And then the rest of the summation here, maybe it's a bit small, but it says that it's all over to all tableau, standard Young tableau of shape mu. So the red sum is over all standard Young tableau of shape mu. And then I'm going to multiply two polynomial two rational fraction in Qt here. So this is a rational fraction in Qt that I'm going to explain to you in a minute. And this is that's a product, that's a monomial. It's Q to the something, T to the something. If you were at Jim talk yesterday, that's what he was denoting, T mu of a partition. So that's not complicated. But the rest, so just to make things clearer, it's nice if you say that for a cell ij in Cartesian coordinates, z of the cell is q to the I, t to the j. That's going to make the notation clear in a minute. Otherwise, we get lost. So that's just a compact way of writing q to the I, t to the j that is interesting. And then I'm explaining to you what is omega of a standard Young tableau. Very simple expression here that hopefully you're not seeing well because it's too small. But I'm going to zoom in a part of it just to give you a flavor of what this is. So this is going to be globally, this is going to be some calculation that gives you a rational fraction in Qt. Okay, so that's the rational fraction. You see it a bit better, but you don't see it well yet. But then I'm going to take one part and zoom into it. So remember, the z something that's q to the something, t to the something else. So this is just a product of qt with some powers. And then you have b and c. B and c are two cells of the diagram of mu, and tau is a standard Young tableau of that shape. So you look at the cell C and look at the value that sits in it, and then you look at the cell B, the value that sits in it, and then you compare these values, they must be smaller. So you do the product, ZB minus ZC. There's a star, don't think about it for the moment. And then you do ZB minus QTZC, ZB minus QZC, ZB minus TZC. So all the four terms are ZB minus ZC, but at the top you're adding a QT and then just Q, then T. So this expression comes up in many places in the shuffle algebra studied by André Negut. It plays a big role, and it's we see it coming up also in calculation of elliptical algebra, and it goes back also to papers we wrote with Adriano Garcia, Mark Kamen, and Glenn Tesler a long time ago. Okay, and I've had it start because if you're unlucky, you might get one of these terms equal to 0. Now, if you see a 0, you just don't write it. Write 1 instead. So star means if this by some bad luck is 0, you put a 1 instead. So no zeros. So there's no division by 0 and no multiplication by 0 in this expression. They're just removed if they could cause you trouble. So that was not the whole of omega, but there are two terms that looks the same. Now there's this other, now the only place where V plays a role is here. And now we're almost done. Don't despair. We're almost done. So this Z something is going to be a Q to something T to the something else. It's just a product of two powers of Q and T. So there's, so let me zoom in as before. So ZC is this kind of power, and then I'm raising ZC to some number, and that number is just the value of the vector V, the famous vector V that comes here. You look at the value of the inside the standard Young tableau at cell C. This is going to tell you where in the vector V to take the power here, and then you multiply all of these for all cells of mu. So that's Z here. So once you calculate all of this mess, what do you get? You get something nice. And now I'm going to consider the case where the vector V comes from tau. A partition. It could be, I'm not even restricting to triangular, but triangular is going to be good later on. So the vector V is just the difference of size of the various parts. So first part minus second, second minus third, etc. And then if you get into trouble because you don't have anything else, you pack with zeros as necessary. And you could start with a partition that has a bunch of zeros at the end, no problem. So n it could be here, could be more than the length of the partition, but then these differences are just going to be 0, 0, 0, 0 at the end. But typically you would take n to be the length of tau plus 1, say in good instances. Now, what happens is that if you calculate a tau with the one that we were calculating with area and dinv, and you calculate it with the negative formula, you get the same answer. By the way, it can be, I forgot to mention it before, but from the point of view of triangular construction and area and dinv, it's easy to see that the polynomial for a triangular partition is the same as for its conjugate, which is also a triangular partition. Maybe it's a bit more tricky to show this in Negut's formula. Did I skip something? Okay, so anyway, now in the paper by Blasiak, Aman, Morse, Kuhn, and Sillinger, that it's mentioned not in only one place, but they conjectured that if the partition tau is concave, and you use the formula the Negut formula that I just showed, it's not the same way it's written in their paper, but it's equivalent. It's a bit trickier to calculate the way they do it, but it's very nice, but a bit trickier. The formula of Negut is easier to put on a computer. So they conjectured that if tau is concave, like this, bounded above by a convex curve, that means that the complement is a convex diagram, then the expression that you get is a polynomial which is positive. By the way, it's always a polynomial in Qt, but it's positive. That's what they conjecture. And but the conjecture that they do is one implication. They say if it's concave, then it's positive. So that's their BHMPS conjecture. And now, for a reason that I won't have time to get to, I thought that it would have to go the other way also. So, and I've computed I've computed up to, for all partitions up to 20 cells. That's some indication. And then the implication seems to be right in the other way. So if you get a positive answer, then the partition is concave. And if the partition is not concave, you get signs. So if it's significant if. So that's very nice, because you get a algebraic description of something and a geometric description, and it's not clear why they should be related this way. Okay, now next step is to expand on this. I'm not finished with my title. I've just showed you the beginning of the story. Behind this story, there's a representation theory. I will not have really time to talk to you about the details of this. And I don't know how to do this for all cases of triangular, but I know for large families. So, this is the real reason why the stuff that I'm going to talk to you about from now on is working. So I'm not explaining this yet, but so I said earlier that these polynomial in Qt would explain as positive linear combination of Schur functions. Now, the reason this would be natural, typically you wouldn't expect this. This is very surprising. The probability of this holding in general is vanishingly small. That's another story. But but if you know that there's some GL2 action here, the 2 because of you have Qt here, then this is forced. And that's the reason why it is positive. So the coefficients here are positive integer. There are multiplicities of the reducibles. That's why you have positivity. But what I want to do is replace 2 parameters by many. And it's not more expensive to go to infinitely many. It's even easier to program on a computer. You don't have to deal with exceptional cases. So I'm going to replace this expression, add to this expression other terms with more parameters. Why I said other terms is because if you take a Schur function that has more parts than 2, then if you put just 2 variables in it, it's going to survive. But if you have a partition with more, maybe my tongue fork. If you take a partition that has more than 2 parts and you put only 2 variables in it, it vanishes. So this expression, if I put just Qt here, some of these terms might vanish, but there are terms that I want to keep more than these. Let me show you. So for all triangular partition, I'm going to calculate an expression like this. That's going to be a positive linear combination of Schur functions. Now, in all of the cases that are here, they're small, maybe to see, but you have the partition tau, triangular, as at most 2 parts. The partition itself. And there's a link between this and the number of parts of lambda. And that's the most number of terms of lambda will be the same number of parts here. So it's going to be 2. And for these partition that I'm showing here. So all of these terms are explained by the previous formulas that we had. But let's go on to other cases. So here you have the first smallest cases where you have triangular partition with 3 parts. And if you look at them, I want you have the Schur expansion of all these A's with triangular partition, but I've added terms here that aren't supposed to be there. These are the terms that I've added. Now, if I put Qt in these Schur functions, all the blue terms vanish. They just go away. But I want to keep them, and there are good reason for them to be there. And they come from this theory with multivariate diagonal harmonics, and I'm going to explain how they appear here in one way. It won't be the whole story because of time, but I'm going to give you one explanation. So let's pick a bigger example to have more fun. So this is the triangular partition 5, 4, 3, 2, 1. By the way, this corresponds to the classical Catalan Combinatorics because you have the staircase here. And if you put Qt in this, some of the Schur function will give you 0. Anything that has more than 2 parts will give you 0. And the one that's going to remain will give you a polynomial in Qt, which specializes at Qt equal 1 into a Catalan number that corresponds to this here, maybe the 6th Catalan number. Now you get a bunch of terms. I put them here in order of partition, typical order of partition, but I'm going to shuffle them up. So that's the same expression, but the terms have been moved around. And what I did is that I highlighted in the first part, so let's forget about these, they're more complicated, but I've highlighted here the terms where you have hooks. So this expression expands into a formula in which you have Schur function. There's some stuff here, but I keep here only the ones where the index of the Schur function is a hook shape. And if you count how many terms there are here, there are 16. There's a 2 here. There are 15 shapes, but there's a 2. So there's the 16 terms here. And there's a very beautiful, nice formula, that binomial style formula that explain all of these terms, but I won't have time to explain. But if you're intrigued, you should look up some of the papers where this is discussed. So this expression, we know we have an explanation for all of these by a simple formula, and it involves Schur function with many parts. You will not have this beautiful binomial type formula if you remove the terms here at the bottom, and so you will only remain a few terms, and you will be intrigued because you don't know what they are. But the simple explanation comes up when you keep all of them. And that's going to be important also in the sequel. So one of the reasons why these things are interesting is because you can explain very complicated calculation using these A tau. So you calculate the A tau, and then out of it, you calculate this whole expression. And this whole expression is a combinatorially reformatted Poincaré polynomial of the triply graded Kovanov-Rosansky homology of a torus link. And calculating these Poincaré polynomial is very complicated, and typically But here we have a simple formula if we agree to use these a tau, because the reason why the tau are needed is because to do the calculation here, I'm going to explain this in the next slide, you need to more parts. And at the end of the story, you put QT. So it's very strange. So the Poincaré polynomial has three things, triply graded. The grading, the triply graded comes from QT and A. Now, EK perp is an operator typical in symmetric function. It's just the dual to multiplication by elementary symmetric function. Let me show you what it does. So you start with some A321, and there's this term, this S111 here, the final term. Now, for each of these, you calculate, you perp with respect to E1, E2, and E3. Now, perping with, say, with respect to E2 means that you look at the partitions here and you remove two cells not in the same row. So here, it's not possible to do this, so this goes to 0. Here, if you remove two cells not in the same row, you'll get S3. Here, you'll get S2, and here, you'll get S1. So that's S3, S2, S1. Here, the expression you get is by removal of one cell. In all possible ways, you get this expression. And here, this final guy, you need to remove three cells, not in the same row. Now, all these terms, which are the QT explained terms, vanish. And the only one that stays is this one, which is extra, which is not supposed to be there, but is a good thing to have. So if you remove this last term, you're not able to get this guy, you're not able to get this guy, and you're not able to get this one. So you will see just portion of the picture if you remove this one. So that's the reason why I want to keep them. But at the end, what you do is you calculate all of this and you put QT in it. When you put QT, this vanishes. You don't need it. You get something here, which is a QT Catalan polynomial. You get here an expression in QT, an expression in QT, an expression in QT. But you will have the wrong expressions if you don't use this. That's the point. So for a more complicated knot like this, you will calculate this. This is what the people that are calculating the triply graded Kovanov homology Poincaré series, they want this. And the point is that you will not get the right portion here if you do not have the information of that extra term. Now, this story is also has an impact in representation theory. Also, it was alluded to yesterday in yesterday's talk by Jim, or questions after, maybe by Brendan. There's lots of things that have been done recently about going from commuting to anti-commuting variables or mixing the two. And from the point of view of physicists, they like it because the commuting variables correspond to bosons and the anti-commuting variable correspond to fermions. So they like what we do because of that. And then this going from commuting to anti-commuting, you can do it without actually going to the anti-commuting, because you can calculate it directly from the expression that you get here. And so just apply the omega involution that changes the partition to its conjugate. So that expression becomes this, and that's the term that does what this term does in the commuting world, in the anti-commuting world. So calculating the anti-commuting version is just free. But you need absolutely this term, because this one is going to give you this S3 here. And that S3 is the story when you have just one variable, for instance, and you wouldn't see what it's doing in that case. So there's a long story here, but I'm going to, I'm close to a conclusion, or more or less. But I want to explain to you how you can calculate these EK perp A nu for any vector V in the QT. So that was the expression that was the people in Kovanov-Rozansky, homology were interested in. You can calculate it with a formula that looks like the Negut formula. And what you need to do is just replace the power that was at the end, the T mu, by another expression also alluded to in another way by Jim yesterday. This is related to the delta operator, and it's the eigenvalue for the McDonald polynomial that corresponds to the delta. But I've avoided using plethistic notation here, in a sense. So you take the elementary symmetric function in n minus 1 minus k, and you calculate it in the variable z that were there before. So at k equals 0, you get back the same expression, because k equal to 0, you have en minus 1. There are n minus 1 variables here. You're forced to multiply all of them. So that's how it goes back to the previous formula. And using this formula, you can calculate all of these without, whoops, sorry, you can calculate these terms directly. And what's fun about it is that if you didn't know that the S11 was there, then, so what I've explained, I've given you a formula to calculate this, to calculate this, to calculate this in Qt. When I calculate in Qt, I get only a thing with 2 parts. For instance, this one has at most 2 parts. But I know that it's supposed to give what happens to this guy when I perp it with respect to 3. So this is the answer of this calculation. So it forces this term to be there. So this way I can build back the required term from this information, or at least part of it, using the formula that I mentioned, a Negut-like formula. Okay, I'm going to rapidly finish with even more. So once you've dealt with paths, then you go to parking function along this path. So I mentioned that you have tau, the yellow shape, and you look at alpha as subshape, and for each subshape of a yellow shape, you're considering parking function of that shape. And so parking function, I simply, if you've never seen the definition, is simply a parking function of a green shape is simply a standard Young tableau of shape alpha plus n cell, a column of n cell, skew alpha. So if you add to the green a column of cells, yellow cell, push them like this, and then skew, remove alpha, then you get a tableau like this, a shape like this, and then if you consider standard Young tableau, this is parking function. So we don't need the terminology parking function if we deal with partitions and standard Young tableau. Now, there's an action of a symmetric group here that I just illustrated by moving the labels around. And that action, if you calculate its Frobenius, it's fun because it gives you exactly the skew-Shor function associated to the shape. And this Q-sure function, in fact, is a product of elementary symmetric function. And that's why these product of elementary symmetric function were essentially mentioned yesterday in Jim's talk, because they have a role here. Okay, and now what we're going to do is we're going to enumerate all these parking functions just the way that Jim did it yesterday. So for all tau is fixed. Now I'm making a more complicated sum than before. I'm summing over all partition containing tau q to the area as before. And now I have a sum over all parking function of that shape alpha. And there's a t to the dinva, the parking function that was explained in some instances by Jim yesterday. And there's a quasi-symmetric function here. And there's a result that says that all of this is going to be a sure positive expression in Qt. Now, if you don't know about div and all that, and you want to calculate this another way, you can use a Nigget-like formula that is just the same formula that we had before, but rather than putting here the product of the z something, you put the Macdonald polynomial h mu. Also mentioned yesterday by Jim, and Jim also mentioned a nabla operator. And what's beautiful about this expression is that applying nabla to EV, V is any vector as before, is just adding to V a vector of ones of the same length. So nabla multiplying or applying nabla a few times, or its inverse, a few times, you can add strings of one or remove strings of one and normalize V to something you would like better. And there are nice properties of this more complicated with many parameters version of here, as before, I've added many parameters with positivity, but I think I'm almost done. So I should finish by just showing you rapidly what this, so we were studying earlier just this guy, and now we study something more richer with more information and more representation theory behind. So there's two groups acting here, the GL something and symmetric group, and you have irreducible characters for the both groups that are involved. And there's a positive conjecture here for these more complicated expression, but I'm going to stop here and mention there's many representation theory things to discuss here, more about this bosonic fermionic situation, and they're linked to Jim's talk yesterday because the operator nabla y that he discussed yesterday applies to all of this stuff very nicely. And that's it. I'm done. That's in French.
Are there any questions or comments?
I had one question. Can you go back to the slide on we had the perps?
The slide of, oops.
Yeah, where you had the E1 perp, E2 perp, all those formulas.
Oh, yeah. Whoops. I'm looking up. So for the A's, I guess.
Right.
Where did I put this? Sorry, it's small. Has to be somewhere here. Yeah, I'm getting there. Oops. Is this the one you want?
That's the one. Wait, no, that doesn't have the perps.
Oh, yeah, no perps. Okay. Here,
There we go. Yeah.
this or the
Yeah.
other way around. Yeah.
So you mentioned that you can deduce, if you didn't know the A321, you just knew the values of the perps, you could get some information. But
Yeah.
I think it's a general theorem that any symmetric function is uniquely determined by its value in all the perps.
You're right, but so the problem here is that when I do the perps, I don't know exactly the whole perp. I know what the value of the perp is on QT. So when I perp something, it might give me something with 3 parts. Then when I put QT in it, this is going to vanish and I won't see it. So that's the reason why I don't get the whole information. You're entirely right. If I knew exactly all these perps, all the terms, then it would be trivial to describe the thing. But the point is that I don't know all of this. I know only its value in QT. So here I cheated because every partition that is here has 2 parts. Now, and I actually gave you, but the formula of Negut that I showed you calculates the right-hand side for the left-hand side, evaluated that QT. That's the point.
So you really don't know, you don't have a formula for the perps.
Not
a full formula.
Not a complete.
Yeah.
No. But there's something funny because say you have more terms. This is a too small example, but if you have more terms, you could calculate from this guy or this guy terms here, and then infer terms down here by going down with a perp. So this way you can build up a lot of information, not only terms with 2 parts, but terms with 3 parts and other, but you don't get the whole picture. Yeah.
Any other question? So I have a quick question. So not homology doesn't give you any positivity thing. I mean, you mentioned
Oh yeah. In not homology, you will have in fact, you get signs when you do the Poincaré series, but the signs are artificial in a sense because they want to have alternating expression. So here I've corrected things using the replacing A by minus A in their formula. But there is some contribution to positivity that you can get from not homology, but not all the tau comes from not homology. So that's why I was saying that you could prove some cases using some technology, right? Either representation theory or homology of not theory, but not all.
Yes. Thank you. If there are no other questions, let's thank the speaker again.
Thank you.